One more. All right, so now 51 through 85 is the short answers. They're going to be in usually little batches like this. You may see something like this where it says questions 51 and 52 relate to this. It may be kind of a one-off question. They're usually in small kind of groups. You may have a diagram, you may have something like in this case, it's a couple sentences, and then a couple of questions will relate to that. They may not be even like related questions. Like looking at this here, I see just something about bright line spectra and then something about electron configuration. There may be questions that sort of relate to each other and they all relate back to the original reading or picture. It may be a reading or picture and then you have three totally unrelated questions that are different from different chapters even, but they all somehow relate to the original idea. Anyway, we'll get through it. There's 35 of them. That's the end of the question, end of the test rather. And we'll see how we can approach this kind of stuff. So it says compounds that contain the element boron, such as boric acid and sodium borate, both have kind of boronish names, produce a green flame when a sample of one of these compounds is placed in a laboratory burner flame. If this flame is viewed through a spectroscope, a bright line spectrum is seen. We did this in lab. We did the flame test. You put the metal salts into fire, turn green and red and whatever, and use the spectroscope, the little kind of viewing device, little plastic triangle-shaped thing, to see the patterns, the bright line spectra. 51 says, state how the bright line spectra of known elements can be used to identify an unknown element whose bright line spectrum was viewed through a spectroscope. So you looked at the spectroscope, you have some unknown element, you don't know what it is, but you can see the line pattern. How can bright line spectra of known elements be used to identify that thing? And that's just that every element's got its own pattern. So I originally wrote on my paper that spectra are specific to individual elements, and you can compare them. When I looked at the official answers to this stuff, it says that you need to compare the patterns. Now it says here, state how the bright line spectra can be used. So they kind of want a strategy, I guess, like what could you actually do? It says compare patterns of the elements. So essentially you would go look up in a book and say, what are these patterns that we know about? And then compare the thing you don't know from your unknown to those known samples to see what actually matches. But every element's got its own pattern of light. You may have a red line, you may have a couple of blue lines. They all have those elaborate kind of like light barcodes almost. So you compare the thing you don't know, the unknown, to what you have and see what it's going to be. 52. State in terms of electrons in shells. So much like we saw in class last week, in terms of electrons in shells. The shells are the rings, the energy levels. So we need to make sure we mention the electrons in those energy levels in those shells in our answer. State in terms of electrons in shells why the electron configuration 221 is an excited state electron configuration of a boron atom. Well, we need to know what excited state means, what ground state means. Remember, the excited state is where the electrons that are normally there just kind of jump out of order. They move around a little bit. So if we go and check the periodic table here, we'll see the electron configuration of boron says 2-3. So the ground state, where the electrons are normally held, typically, the usual arrangement of stuff, is 2 electrons in the first ring, 3 electrons in the second ring. What it says now, it says this is an excited state. It's telling us in the question, this is what the excited state is, and it says why. The excited state is now 2-1-1. 2-2-1. So 2 electrons in the first ring, 2 electrons in the second ring, and 1 electron in the third ring. So why is this an excited state? It's just because the normal configuration is to have 2 electrons in the first energy level, 3 electrons in the second energy level. Well, when we look at this, what changed about it? It looks like one of these 3 outer ring electrons sort of jumped up and made a new ring of its own. So instead of having 2 in the first ring, 3 in the second, now you've got 2 in the first ring, 2 in the second, and one of those original 3 jump up to a new place and made a new layer. So we have to say something to the effect of, its ground state has this, 2-3, so the electrons moved out of order. In terms of electrons in shells, you could say the electrons that used to be in the second shell, one of them jumped up into a third shell and made a new layer, made a new ring, something about that. If you just basically compare these two situations in terms of their electrons, you're good for an answer. One of the electrons in the second ring made a new ring. One of the electrons in the second layer got excited and went to the third level, something like that. But that's why it's excited. All right, those 2 questions. Next little batch of 3 questions now with this picture. And tells us here 53 through 55 are all based on this thing at the bottom. Silicon is an element in group 14 on the periodic table. It's group 14, that's the 14th column. The atomic mass and natural abundance for the 3 naturally occurring isotopes of silicon are shown in the table below. So the isotopes, it was just one earlier multiple choice question. Those are different versions of the elements. One weighs a little bit lighter, one weighs a little bit heavier, based on different numbers of neutrons. So the table here shows you there's the version of silicon we call silicon 28, which its mass is actually 27.98, just round to 28. The version of silicon 29, which its actual mass is 28.98, again, round up to 29. And the version of silicon we call silicon 30, which has an actual mass of 29.97, so again, round up to 30. And then natural abundance is just how common these things are. They're not like total coin flip anywhere you find silicon is going to be one or the other. The version that weighs 28, the 27.98 version, that's going to be 92.22% of all the silicon anywhere in the world. And then much less is these other two options. So these are going to be much less common, much more rare versions of silicon apparently. 53 says draw a Lewis structure for an atom of silicon in the ground state. So atom means it's neutral, ground state is normal, nothing going on. We can draw these electrons. So we have to go look up, see what we find about silicon. We look on the periodic table. We're only drawing the valence electrons. So for silicon, there are 4 valence electrons, it says right there. So we're going to draw our symbol Si. We're going to draw 4 valence electrons. I don't know why they made this silicon. I hate it when they use elements like this because the dot of the I can be confusing. It looks like it's one of the electron dots. So I'm just going to draw my electrons a little bit differently just to differentiate them. And we always draw 2 up top to start. There's 1, 2. And then my third is going to go on the right. My fourth will go on the bottom. There's your 4 electrons. Usually I just do the dots. But again, just because that I has its own dot as part of the letter, I just want to make it look a little bit different. If you want to draw them as regular dots, that's fine. But just be clear, like don't draw it right next to the dot from the I. Don't get confused by that one. Make it clear what dots are what. 54. Compare the energy of an electron in the first shell of a silicon atom, the first ring, to the energy of an electron in the third shell of the same atom. Compare just means you're going to say something like, this one's greater, this one's less, this one's bigger, this one's smaller, something like that. Energy of something in the first shell, the first ring, to energy of an electron in the third shell. Every time you're moving out from the nucleus, the energy increases. Electrons right around the nucleus in that first energy level have some energy. Electrons in the next ring out have more energy. Electrons farther out have more energy. That's why when you start to get excited electrons, they jump up levels. If you have your nucleus right here, and you have the first ring, second ring, third ring, right? Something like this absorbs energy. It takes that extra energy and now jumps up to a higher level because it can't hang out where it was anymore. I know my circles are totally off balance, that's fine. You gain energy, you move to a higher ring. When you release that energy out again and lose the energy, that's when you drop back down to the ground state again in the lower ring. So anything in the third ring in this case, the third shell, is going to have more energy than something in the first shell. We don't even know exactly how much. Just third shell, electrons have more energy. I'll write a complete thought, then first shell, electrons. Done. Any way you want to phrase that. If you want to say first has less energy, third has more energy, whatever. Showing numerical setup for calculating the atomic mass of the element silicon. So calculating the atomic mass. Masses are averages. We have 3 versions of silicon here. One that weighs 27.98, one whose mass is 28.98, one whose mass is 29.97. And they have different abundances. One is 92.22% of all the silicon, one is only 4.69, one is only 3.09. So you have to show some kind of setup. It doesn't say calculate, it says showing numerical setups. You just have to show how you would do the math. So essentially you just have to fill in, you'll have a big blank spot in your answer key, big blank box to fill in, and you have to show the setup. So there are 2 different ways to do this. I'm going to try to make room here in my paper. My answer key, I did it poorly, so I'm going to try to space this out a little bit better so I know everything's actually going to fit on here. Let's see, how am I going to space this? Let's do... it's going to be easiest to do. Okay, let me do it this way. There's the 2 ways to do it. You can either do the mass times the abundance, how common it is, for each one of these things. So in this case, you do 27.98 times 92.22, and then 28.98 times 4.69, and 29.97 times 3.09. You can do that, add them all up, and then divide by 100, or you can do a little bit different of an average. So I'll do the first one first. So we're just going to go one at a time. So I'm taking the actual mass, the actual more precise number here, not the rounded 28 version. I'll take the 27.98 number and multiply that by the percentage. So you're doing the mass of the one version times the percentage that counts. and that's going to be the mass of the second type times percentage it counts, and so on. This is actually kind of uncommon to even see 3 different versions. Usually you see 2. Like, usually that's where the top's out. They don't make you do too much on the Regents. I'm surprised it's 3 here, honestly. And that fact, they have to actually write this out. A lot of times this will be a multiple choice question where it's just you find it in the list. So whatever. We're going to do 27.98 times 92.22. So 27.98 times 92.22. All right, I'm going to put that in parentheses because I'm going to add the next one. I'm going to do 28.98 times its percentage, 4.69. And I'm going to do the next one, plus 29.97 times its percentage, 3.09. All right, close parentheses. So you've got the mass times the percentage for every one of them. So you can do this multiplication here, you do this multiplication here, you do this multiplication there, add those 3 numbers up, and then just once you do that, the whole thing divided by 100. That's one way to do it. That's fine. The other way to do it, and I'm going to hope this fits on the not much space I have at the bottom of the page here, is you can skip this divide by 100 step at the very end by converting these percentages to decimals at the beginning. That means you're going to take the same mass numbers, but instead of multiplying them by this percentage, 92.22 and 4.69, 3.09, you convert these percentage numbers to decimals by just moving the decimal point 2 places to the left, which accomplishes the exact same thing as dividing by 100 at the end. So what that's going to look like is 27.98, right, that's the number from here. Instead of multiplying by 92.22, I'm going to move this decimal 2 spots to the left, and I'm going to multiply it by 0.9222. For the next one, again, 28.98 times, and I'm not going to multiply it by 4.69. I'm going to move the decimal point 2 to the left, and it's going to be multiplied by 0.0469. And same thing here, 29.97. I'm going to multiply it not by 3.09. I'm going to move the decimal point 2 to the left and multiply it by 0.0309. And now just add those 3 numbers up. You don't have to divide by 100 at the end because you already essentially divided by 100 during the math when you move that decimal point. You're going to get the same answer each way. Whichever way you do it works. Just really, in this case, it really should have been like 92.22% times 4.69% times 3.09%, if we're being more precise. And then divide by 100. In this case, you convert to decimal first, and then one from there. That's how you do that. You don't even have to get the answer. If you go the next step and get an answer, great, but you don't have to. It only said show the setup. Okay, number 56. I'm just going to check my pen because it seems like it might be running out of ink. Looks pretty good, actually. Okay, I don't know. It's just gotten dry. All right, the unbalanced equation below shows a reaction between nitrogen monoxide gas, that's the NO, and oxygen gas, O2, to produce nitrogen dioxide gas, NO2. So that's your equation. It says it's an unbalanced equation. So these are not the same amounts of stuff, which makes sense because I've got an N at the beginning and at the end, but I've got 1, 2, 3 oxygens at the beginning, only 2 oxygens at the end. So it's not totally balanced. Number 56 says, state in terms of reactants and products why this reaction is a synthesis reaction. So you got to remember what a synthesis reaction is. Synthesis reaction is when things come together, when 2 reactants or more than 2 or more, join up to make one product. So in terms of reactants and products, you have to say, why is this a synthesis reaction? So you could just write, there's more of the reactants than products, your reactants form up. I'm going to say 2 reactants, I'm going to be pretty clear on this, 2 reactants combine into one product. I mentioned reactants, I mentioned product. 2 reactants, 2 different things on the left, combine into only one type of thing on the right. There it is. 57. Balance the equation in your answer booklet for the reaction using the smallest whole number coefficients. All right, so in this case, your answer booklet often will just have, one line or 2 lines to fill stuff in. So like for this number 56 you just did, it'll give you the question on your test, just like this is obviously the only test paper. This is the paper you'll have, and then your answer booklet will be the separate book you're going to answer it in, and it'll have 56, and then it'll just have some lines. It'll probably have 2 lines. So it's not, you don't need to write a long answer. It's showing you by the amount of space they give you how much answer you should write. It'll probably have just 2 lines. The length of the page, it's not a lot of space. Even if you really, really overworded things, you're not going to be able to take up too much space there. For 57 now, it says balance the equation in your booklet. So your booklet will actually give you the equation like this. So it'll give you 57, and then it'll have, space NO plus space O2 goes to this little line to fill in, and NO2. So it'll have like that, and then you have to balance it like we did in class earlier in the year. And you can take all the space you want. You can do your math stuff, you can do your figuring out, but you'll just have to fill those numbers in. Everything is pre-printed. You just have to put numbers on the line. So remember, you're always going to write something, even if you don't have anything to write. You're going to write a 1 if it's a blank line. You're not going to leave anything blank. No one's going to get confused. So let's go through this. We have to count some stuff up. On the left side, I have one of the ends right there. And on the left side, I have 1, 2, 3 auctions. So this is going to be kind of a weirder looking question than we're probably used to, just because auctions in more than one place. We may have to play a little game here. It's going to be solvable, but we may have to kind of do a strategy. Right side N is 1, right side O is 2. All right, so where do we start? Well, nitrogen is already balanced. Typically, I leave oxygen for the end. I leave hydrogen by the end for the end if it's there. I usually leave any element that's by itself for the end if I can. In this case, I really can't do that because I only have 2 elements, and the oxygen is the one that's unbalanced. Nitrogen already is balanced, so I have to start with oxygen. So I'm going to try to make sense of this. 3 oxygens over here, only 1 oxygen or 2 oxygens on the right. Any number I put on this line is going to change all the oxygens at the same time. If I want to change the oxygens on the left side of the arrow, I have to worry about 2 different molecules. It's going to be a little bit trickier. So I'm going to try to get to some number that's going to make sense, and I'm going to aim for 4. I see 1 oxygen and 2 oxygens and 2 oxygens. 1 and 2 both go into 4. I'm going to try to add up to 4. So if I do that, I'm going to make this a 2 to make this be 4 oxygens. I also changed my number ends, so I'll just change that while I'm here so I don't forget. Over here, if I want to get this to be 4 oxygens, the easiest way to do this, I'm going to make a 2 right here. That changed the number of ends, sure, I'll fill that in just because I did it, but this makes the oxygens 2 right here, and with these 2 oxygens, they add up to 4. And now everything's balanced. It's kind of a weird question. It's not particularly difficult, but it's a different kind of style. Just kind of play around with the numbers. It works. You can try it. And then this one is blank, so I'm just going to make that a 1 so I don't forget anything. So 2, 1, 2 is your answer. 2 nitrogens to start, 2 nitrogens at the end. 2 oxygens here, 2 oxygens here is 4. 2 times 2 is 4 over there. Everything's balanced. 2, 1, and 2 cannot be simplified, so that's your answer. Let's put a little check mark up here so I know I did it. 58, determine the percent composition by mass of oxygen in the product, NO2. And it tells you how much NO2 actually weighs. I think I'll do my math at the bottom of the page just because it's going to give me a little more space. It said percent composition. The percent composition formula is on the back page of the reference table. We saw that in an earlier question, but it is the one right there. It's going to be part over the whole times 100. So I'm going to go fill that in. Part over whole times 100, and it said in the question, determine the percent composition by mass of oxygen. So how much oxygen is in this molecule right here, NO2? The nitrogen is only 1 of, the oxygen there's 2. So the top part of my fraction is going to be how much 2 oxygens weigh. That's going to be the mass, the part rather. And the bottom part, the whole, if you want to, you could add up N and O2, but you don't have to because it tells you right here in the question that the total mass of the whole thing is 46. So my whole in the bottom is going to be 46. My part, I have to figure out what 2 oxygens weigh. When I go to my periodic table, it tells me that each oxygen weighs 16. Let's turn to my page. I can show you that in 1 second here. Remember, it had NO2. Each oxygen weighs 16. So if I have 2 of the oxygens, they're going to weigh 32 total. All right, so that's my part over whole. And now I'm just going to times by 100, and I should get an answer. And when I do that, it's going to be about 69.6% I had. If you want to round that to 70%, either way, the answers that we were told to accept, I think we're anywhere from 69.5 or something up to 70. So either of those works as an answer. So that is number 58 now. Hold on. All right, number 59 and 60 now have this little chart here. And it says the radius for ions of these four elements from group 17. That's the halogens, the halides. As ions, how big are they? So they all have gained an extra electron, and they have this ionic radius. So 59 says identify the noble gas that has atoms in the ground state with the same electron configuration as Br ion in the ground state. So which element, which noble gas normally has an electron configuration like Br with a minus charge? Well, let's see what Br with a minus charge will look like. When we go find Br, Br's normal electron configuration says 2, 8, 18, and 7. So it normally says 2, 8, 18, 7. But we know it gained an extra electron here, so it's actually going to have 8 electrons in that last ring. That's that octet rule. It got the 8 at once. So now the question's asking, which noble gas normally looks like this? So we just have to go to our periodic table and see whose electron configuration is 2, 8, 18, 8. We could just go through. We know it's noble gas, so it's going to be the last column. We can actually get kind of a head start if you want to confirm your answer. Add up your electrons. 2 and 8 is 10, plus 18 is 28, plus 8 is 36. So it should be element 36. And when we look at element 36, krypton is 2, 8, 18, 8, just as we expected. So krypton is our answer. The normal electron configuration of krypton is what bromine is going to look like when it gains an extra electron. 60, state in terms of electrons why the ionic radius of a group 17 element, like this one's in the chart, is larger than the atomic radius for that same element. In terms of electrons, what changes about its electrons? Why are these ions bigger than the things they started out as when they were uncharged? Well, they're gaining electrons, they're going to the valence shell. That's what's happening here. So they gain extra electrons in the valence shell. Or it should be 1 extra. I'm going to write 1. Gain 1 extra electron in the valence shell. That's it. In terms of electrons, what's different? The only difference is they gain extra electron. So just write they gain extra electron. And give me 1 sec because my battery is dying, so let me just plug this in. Where'd that go? There it is. Next page, 61. Diagrams of gas. It says diagram below represents 2 sealed rigid containers in conditions of pressure, temperature, volume are each given. One is N2 and other is O2. Doesn't really make a difference. All right, 61. State in terms or explain in terms of strength of intermolecular forces why the gas in container B has a higher boiling point than the gas in container A at standard pressure. So intermolecular forces. Talked to them earlier in one of the multiple choice questions. Intermolecular forces are when they attract to each other. They hold on to each other really tightly as a liquid. And if you have weaker intermolecular forces, they're not holding on to each other as well as a liquid. They're going to turn to become a gas more easily. If it's stronger intermolecular forces, they're not going to become a gas as easily. They're going to stay as a liquid. They're going to stay as a solid even. So state in terms of strength of intermolecular forces, why is container B a gas under normal conditions while sample A has a higher boiling point than sample A. Sorry. So gas in container B has a higher boiling point than gas in container A. So you need to get container B's gas hotter, give it more energy to make it become a gas from the liquid phase. So the stuff in container B, oxygen, needs to absorb more energy. You need to give it more heat to get it to become a gas. Why would it need to absorb more heat in terms of its intermolecular forces? Sample B is holding tighter to itself. The attractions in O2 are stronger. The intermolecular forces between O2 molecules are stronger, meaning you have to give it more energy. They don't want to separate from each other. They don't want to break away from each other. They're happy. They're holding on to each other. So O2 in container B has stronger intermolecular forces. Than N2 in container A. It holds on to itself more strongly, so you need to give it more energy, has a higher boiling point. In Space Your Answer booklet, show a numerical setup for calculating the pressure if the gas in container B is cooled to standard temperature. So calculate the pressure. We look at this, it gives pressure, temperature, volume. This is going to be one of those PTV equations. So we turn to the reference table back page. We get our combined gas law right here. P1 V1 over T1 is P2 V2 over T2. So I'm going to go write that for myself. P1 times V1 over T1 equals P2 times V2 over T2. And this is one of those things where it says, show a numerical setup. We only have to show how we would set this up and calculate. We don't have to actually calculate. If you want to go forward and do it, it doesn't make a difference. But once I see that you've correctly plugged in the numbers properly, you're getting the points. It doesn't matter if you even get the right answer or not, because you don't have to. All right, so let's look at container B. So what do we know about container B? We know container B has a pressure of 101.3 kPa. So that's my starting condition. Pressure is 101.3. The starting condition, the volume was 750. So 750 is my V1. And the temperature was 298 K. Just remember, temperature for these questions has to be in Kelvin. It is, so we don't have to convert anything. If it was in Celsius, we would just have to remember to convert to Kelvin first. All right, so there's my pressure, volume, and temperature to start. And I'm going to plug it in for the new conditions. It says calculate the pressure, so we don't know what the pressure is going to be. So I'm going to leave that as P2. And I should have two other values here. It says container B is cooled to standard temperature. So we got to change the temperature to standard temperature. So let's see what standard temperature actually is. We got to go to our reference table. Standard conditions are on the very first page. And standard temperature tells us in Kelvin is going to be 273. So that's going to be our standard temperature. That's going to go on the bottom. It goes from 298 down to 273. It says it was cooled, so that makes sense. It dropped from 298 to 273. We're still missing a number though. We changed our temperature. We're looking for the new pressure. We don't know what the volume is. Does it say it here? It says calculate the pressure if the gas in container B is cooled to a standard temperature. It doesn't say anything but the volume. So let's go back and check the question, see if we can find an answer to this. I noticed the volume is the same in each question, each container, and that's because right up top it says diagram represents two sealed rigid containers. These are like solid, probably metal containers. The volume's not changing is what that means. So the volume's going to be the same. So you can just leave the volume exactly the same as 750. That's fine. This is an answer right here. This answer is good. That's going to give you points. If you want to say that the volume is the same and we're just going to leave it out because standard stuff, or constant stuff I should say, doesn't count, you could just cross off 750 each side. That works fine. So 101.3 over 298 equals P2 over 273. That's a good answer too. Either way, that's your answer right there. You don't even have to do the whole math. Next page, 63. We've got a table now. So this table below shows the formulas of 3 organic compounds. These are some things we would have seen recently, some stuff like this at least. And a chemical name for 2 of the compounds. So you've got this formula over here. This is the structure formula. It tells you what the structure actually is, what the shape is, gives the name. This one it shows us does not give a name. This one gives a structure, does give a name. 63 says, identify the element in these 3 compounds that allows them to be classified as organic compounds. It tells you all 3 of these things are organic compounds and what makes them organic. What is the element that does that? It's carbon. That's it. Carbon is always the thing that makes something organic. If you forgot that, hopefully you remember there are the organic charts in the reference table. You got this table right here, organic prefixes. You got the hydrocarbon series here, and I mean this table shows you that the name depends on the number of carbons. So hopefully, even if you forget this, you're going to look here and say, "Oh, right, it's carbons. That's the important thing. I'm paying attention to the number of carbons. That must be the really important thing." A lot of times, a question like this will be a multiple choice question. We saw one the other day in class. You were doing the old test that said which element can form chains and rings and stuff. But carbon's the important one. So you can write C, you can write the word carbon. That's the only one. It's not carbon and hydrogen both. It's just carbon. That's what you care about. 64, identify the class of organic compound to which compound 1 belongs. Here's compound 1 right here. Which type of compound is this? Which, what was the wording? Which class of organic compound? So that is the other table. I just had this chart right here. We have the organic prefixes and the hydrocarbons. I'm just going to turn to the next page over. And that's this whole long table. Table R, where it has all the functional groups. So compound 1, we want to see what kind of molecule is this. So remember, when we're doing this, we want to see what's the extra stuff that's not just a chain of carbons with some hydrogens. What's the different thing here? So if I look at this picture, you can even look at your chart and say, well, does it have fluorine or chlorine? Does it have this OH piece? Does it have an oxygen between two chains? Does it have a double bonded O at the end? Does it have double bonded O in the middle? Just see what's different. I notice here, there's an oxygen in the middle here between, looks like a carbon chain over here of 3, another carbon chain right here of 4. Actually, there's another carbon right there. And I've got this oxygen with another double bonded oxygen hanging on that kind of more central carbon. So I'm going to see if there's something like that on this list. A double bonded oxygen with another oxygen in the middle of 2 carbon things. And when I go through here, that's not this, it's not these two, it's not this, that's not the same, this isn't the same. If I kind of move my picture over here, maybe I'll get them both actually. Let me slide that over here. I'm looking for that kind of thing, double bonded oxygen with another oxygen. And I see that right here as an ester. Here's the carbon with a double bonded O. We see that in the corner up there. And it's also got that second oxygen by itself that keeps going. And it's got this name that says methylpropanoate. It's got that weird O8 ending. And if I look here back on the chart, that's exactly what this looks like. It's got the ill in the first word and then the O8 ending on the second word. So that's going to be the one. That's going to be the type of thing. So those types of molecules are called esters. That's what our answer is. Identify the class of organic compound. I'm going to write that this is an ester. Done. All they are going to match it up. Write a chemical name for compound 2. So what would we call this thing right here? Compound 2 is the picture, not the name. So once again, we just want to see what's different. We see this carbon chain, it's got 1, 2, 3 carbons. That's like the normal thing. And then what's different? It's got this double bonded oxygen, and it's got an OH on the last carbon in the line. So let's go right back to the table we just had a second ago, and we're going to see who has a double bonded oxygen with an OH at the end. Not these. This is OH but no double bonded oxygen. Doesn't have any of that. This looks kind of like it's got the double bonded oxygen, but then it's just an H, not an OH. That's not right. Ketone is not it. Oh, here we go. Organic acid. Double bonded oxygen with an OH. There's nothing else coming off the other side. This is what we're looking for. So organic acid. How do we name organic acids? It gives us the little clue here, a little reminder example here. It says propanoic acid. If I look at this molecule, I see 1, 2, 3 carbons. So that's where the prop comes from. And it looks like oic acid. We're just going to change the ending of the name to be oic acid. So this would have been 1, 2, 3 carbons. It would have been called propane. So they changed the ending to propanoic acid instead of propane. So let's do the same thing here. And when you know it's the same exact molecule. 1, 2, 3 carbons. Again, it would have been propane, but now it's going to be propanoic acid. Instead of propane, we change that E to an O and make it propanoic acid. So let's write that again down here. A lot of the times you'll see that where the molecule is the exact one in the reference table. Just double check, it's probably there somewhere. Propanoic acid. Next page, 66. Oh, we got some stuff to read here. Okay. I'm no more thrilled about it than you are. Periodic table of the elements has changed over the past 150 years. During this time, many elements have been added, yada, yada. This happened only a couple of years ago. I remember when we had to update all the reference tables. The elements 113, 115, 117, 118, all these guys. So when you're looking on the reference table, it talks about the periodic table, you can just check them. It says 113, 115. These are all these ones down here. So when your reference table came out in 2011, these elements have not been named yet. So these are when they just have these kind of these little like symbols here, these kind of fill in the blank filler ones. So 13, 115, 117 is saying all these elements down here at this point in time now do actually have names. Back to this, it says some stuff about them. It says they were named 2016, their names were approved, all this stuff, and the table below lists the names, symbols, and everything else. So that's just these. So these 4 elements now that were at the very bottom, now they have names. These are the updated names. So on here, they're just these kind of placeholder symbols. Now they actually have their own symbols and these names, which are right here. Here's your symbols, here's your names, here's your topic numbers. All right, so number 66 says, identify the element in this table that's located on the periodic table in the group classified as noble gases. So which of these 4 elements is a noble gas? Well, we know noble gases are the last column in line. So let's just see which of these 4 elements is actually there. You got 113, 115, 117, 118. 118 is the one that's noble gas. Done. It says identify the element, so I'm going to write the actual name, oganesson. I have no idea where the name comes from. It's symbol OG. You could write it's number 118, whatever. I would take any one of those things. Do not write UUO, that's the old symbol, but maybe we would debate in the room whether that's a good enough answer. I would say not to. Just write the real name. It says which one. So you now know what it's called. Call it that. 67, in terms of valence electrons, why is the element nihonium and the element tennessine expected to differ in their chemical properties? So why would you expect nihonium and tennessine to be different in chemical properties? In terms of valence electrons, what do we know about valence electrons and chemical properties? I remember that valence electrons determine the chemical properties. That's why things in the same column act the same way, because everything right here all have 8 valence electrons. They're going to act very similarly. All these guys have 6 valence electrons. They're going to act very similarly. So I wonder if it's something like that. It talks about nihonium and tennessine. So nihonium is number 113, and tennessine is element 117. So let's go check elements 113 and 117. Well, that's in this column, so I'm assuming it's going to have 3 valence electrons like everybody else. This guy's all the way over here in group 17, has 7 valence electrons like everybody else. So why would they behave differently? Why are they assumed or expected to not have the same chemical properties? Because they have different numbers of valence electrons. In terms of their valence electrons, they have different numbers of them. Different numbers of valence electrons. Done. Describe the general trend in ionization energy, first ionization energy, which is on the reference table, as the 5 elements above moscovium in group 15 are considered in order of increasing atomic number. So the 5 elements above moscovium in group 15. So moscovium is number 115. It's talking about the 5 elements above that in group 15. So the 5 elements above 115. We're looking at these 5 things right here. N, P, A, S, S, B, and Bi. Those 5 elements. It says describe the trend in ionization energy as those 5 elements are considered in order of increasing atomic number. So as you consider these 5 elements, top to bottom, increasing atomic number, 7 to 15 to 33 to 51. As you consider these 5 elements going top to bottom, it says describe the trend in ionization energy. You just got to look it up. It's on that page after the periodic table where all these numbers are. There's ionization energy right there. So we're just going to look this up. I'm just going to make a little list for myself first so I can actually write this. The 5 elements we're looking at in group 15 are nitrogen, it's phosphorus, it is arsenic, antimony, and bismuth. All right, so I'm just going to look up those 5 elements' ionization numbers. Ionization energy, rather. So first, ionization energy. Nitrogen was the first one we had. So here's ionization energy. Nitrogen is 1402. And we're just looking to describe the general trend. So we're just looking what's the pattern. For phosphorus, the ionization energy, it says, is 1012, 1012. So right away, I see the number went down. Let's see if that continues. Arsenic, AS, where's AS? It's down at the bottom here. AS says its ionization energy is 944. My pattern continues to be the numbers are going down, decreasing. For SB, that's going to be on the next page. So let's find SB. Where is SB? SB, antimony says 831. And it's pretty clear what the pattern is at this point. But let's finish the last one. BI, where is BI? BI should, oh, at the bottom, there it is. It's 703. So what's the pattern? What's the trend? 1402, 1012, 944. Our numbers are decreasing. So you could write, I'm going to write ionization energy decreases. That's the pattern. That's the trend. 69. State in terms of protons. We have to talk about protons in our answer. Why tennessine, this element right here, is listed before oganesson in period 7. So why is tennessine at number 117 listed before oganesson at number 118? Why is 117 before 118 in terms of their protons? Well, the periodic table goes in order of protons. So just write This guy has 117 protons. This one has 118 protons. That's it. I could write tennessine, that's element TS, has only 117 protons. Oganesson OG has 118. Some answer like that. Tennessine has fewer protons. Oganesson has more protons. Tennessine has one less. Oganesson has one more. Whatever. The elements go in order of protons. So if you're 117, you have one less proton than something that has 118. Right there. Next page. Hydrogen gas is needed for many industrial chemical reactions. An equilibrium system. I hate this question. I looked at this the other day and said, why would they write this so poorly? Actually, it's the question at the bottom, not this writing. But an equilibrium system that includes the use of a catalyst produces hydrogen from methane and steam is shown in equation 1. So this equation, you're taking this methane, CH4, you're adding some water to it, some energy, it's making carbon monoxide and hydrogen gas. And then this system, it says, makes hydrogen gas in this other reaction. 70 says, compare the rate of the forward reaction to the rate of the reverse reaction for the equilibrium system at equilibrium represented by equation 1. They keep using this phrase equilibrium system at equilibrium. Stop using the word equilibrium. Why have to be difficult? Just use normal English. I don't know. Compare the rate of the forward reaction to the rate of the reverse reaction. That's what you really need to say. Compare the rate of the forward reaction to the rate of the reverse reaction, and it says at equilibrium. You need to know what equilibrium means. At equilibrium, your forward and reverse reaction rates are the same. Your amounts stay constant. So in equation 1, your amount of CH4 is going to be whatever it is. Your amount of H2O is going to be whatever it is. They don't have to be equal to each other. Just whatever their amounts are, their concentrations are, they're going to stay the same. Stay constant. Whatever your amount of CO is, that'll be constant. Whatever your amount of H2 is, that'll be constant. But your rates are equal. If you want to write forward and reverse rates, go for it. But they're equal to each other. 71. State how the equilibrium shifts when the temperature of the equilibrium, this is the one I was saying, it's just, why do you have to keep using the word equilibrium? It's just overdone. State how the equilibrium shifts. So is it going to shift to the right, shift to the left? Is it going to go forward, go backwards? When the temperature of the equilibrium system at equilibrium, represented by equation 1, is increased. It's saying in equation 1 right here, which way is the reaction going to shift if temperature is increased? That's what it's saying. If you increase temperature, you're increasing this energy right here. It's on the left side of the arrow, so if you increase this amount of stuff on the left side, remember, add away, take towards. Once again, my paper is going all over the place. Apologize for the sloppiness. It's not just my terrible handwriting, it's also the paper popping up. Add away, take towards. So if you're adding temperature, increasing heat, you're adding to the left side, it's going to move away, you're going to shift to the right. You're going to try to use up all the extra stuff you just added on the left to make more of the product. So state how the equilibrium shifts. It's going to shift to the right. You can say it's a forward shift, it shifts to the right, either way. State in terms of activation energy. Activation energy is a little like a boost you got to give it to make it start. Why the catalyst increases the rate of the forward reaction. It always lowers the activation energy. Catalysts lower the activation energy. Always. That's where you have that potential energy diagram like this. And you got your curve, whatever your curve is going to look like. And the catalyst is always going to be that little like dotted line that's going to go like this. It just lowers the hill. You start and stop in the same places, but it lowers that hill. You don't have to use as much energy anymore. Always lowers activation energy. 73. On the labeled axis in your answer booklet, draw a potential energy diagram for the forward reaction represented in equation 2. So again, it says in your booklet, you'll have a thing in your booklet looks kind of like this. It's going to say 73. Let's count this blank thing. When I looked at the actual answer key, let me find the actual thing it said. It's going to say reaction coordinate. That's essentially just saying time. You know, how is the reaction proceeding over time? So reaction coordinate down here. We'll have the little blank axis there. And then it'll say potential energy on the other side like that. And it says Draw it, label it to draw a potential energy diagram for the forward reaction in equation 2. So, well, let's look what equation 2 looks like. I'm just looking for where the energy is. In equation 2, energy is on the right side, so I know I'm losing energy. It's going to be exothermic, so I just need to draw a picture on the bottom here that's some kind of exothermic diagram. So I'm just going to draw it something like this. It's going to go up that roller coaster hill, drop down, end up lower than where we started. That's it. I'm done. Nothing else. I start up here. I end down here. It's got that nice kind of curving slope upwards, drops back down again, and ends lower than where we started. It lost energy. That's all you have to do. Nothing else needed. 74. It says it's got a operating voltaic cell. This is the battery. We had the song with this. We did a bunch of drawings with these things. 74 says, state the form of energy that's converted to electrical energy during the operation of this voltaic cell. Batteries use chemical energy to make electrical energy. The chemical reaction taking place between iron and copper, in this case, that's the two metals they happen to draw here, that produces electricity. Electrons moving from one to the other, that makes the electrical current. So state the form of energy, it's chemical energy, gets turned into electrical energy. The opposite's true in the electrolytic cell, where you need to use electrical energy to make a chemical reaction happen that wouldn't happen on its own, like when we silver coat something or gold coat something, silver plating, that kind of thing. 75. Identify one metal from table J more easily oxidized than copper and less easily oxidized than iron. So remember on table J, it says table J, so we should be automatically turned there anyway, but let me flip back to table J. Table J is where all these metals are listed, and remember the higher up a metal is, the more easily oxidized it is. The lower down, the less easily oxidized it is, or the more easily reduced. So if this is saying it wants a metal from table J more easily oxidized than copper, it means it's going to be higher than copper. So I'm looking for something higher than Cu and less easily oxidized than iron. I'm looking for lower than Fe on table J. So I just got to go to table J, find something between Cu and Fe essentially. So we're looking something higher than Cu, so higher than here. Now just notice it said a metal in the question, so H2 doesn't count. And it specifically says in the answer key, don't accept H2, because that's not a metal. That's just there to compare. But higher than Cu, so really we're saying like higher than here, and lower down than iron, so lower than here. Any of these four elements works. But just be careful. It says identify one, and one is italicized. If you write more than one of those metals, you're getting it wrong. We're specifically told do not accept more than one answer. So just write either CO, Ni, Sn, or Pb, and you're good. So I'm going to do the same thing right here. CO, Ni, Sn, or Pb. Write one and only one of those answers, and that's right. 76 says, state the purpose of the salt bridge in completing the circuit in this cell. What is the salt bridge there for? Salt bridge is there to let ions move. It lets ions migrate or move. And I'm going to leave it as simple as that. I'm not giving any more detail about where they're going, where they're coming from, just ions can move through the salt bridge, that's it. Electricity moves through the wires, electrons move through the wires, ions move through the salt bridge. 77, write a balanced equation for the half reaction that occurs in the copper half cell. What is the half reaction, oxidation or reduction, whichever one happens, between copper? So I just see up here, we've got this diagram of what the picture actually looks like and what's going on in the battery, but also underneath it tells us the equation of what's actually going on between iron and copper. So it said copper, I'm just going to focus on the copper part. It tells us we start with copper plus 2, and we end with copper neutral. So I'm going to write that down here. We're going to do our half reaction. We're doing copper from a plus 2 charge, going to neutral copper with no charge. Half reactions are where we write electrons into one side or the other based on what's happening here. Remember, you always pick the more positive side. Plus 2 is obviously more positively charged than Cu, so I'm going to write on this side Cu with a plus 2 charge, plus some number of electrons to go to copper uncharged. Well, it's going to be 2 electrons to make this plus 2 charge look like the neutral one over here. So Cu plus 2 gains 2 electrons, and that turns into the uncharged neutral version of copper. That's my answer right there. That's my half reaction. And that is reduction in this case. It's going from a plus 2 down to a 0 charge for copper. Iron should have been oxidized, and we look back here, plus 2 to plus, 0 plus 2, that it was. Yeah, iron was oxidized, copper was reduced. Iron's higher up, it gets oxidized, copper's lower down, it gets reduced. Next page. last page, actually. Lots of questions thrown off the last page here. Sometimes it's like this, where it's like 6, 7, 8 questions on one shot, or other times it's just they kind of load up and you'll have like 2 questions last page. It doesn't really make a difference. All right, in the lab investigation, 0.010 molar NaOH, that's a base, solution with a pH value of 12, that makes sense, bases have high pH numbers, is used to determine the molarity of HCl. It's an acid, so it's an acid-base titration. We did this in the lab. It had the indicator, we had the big tubes, the burettes, and we added acid and base to each other. A 10 milliliter sample of the HCl acid is exactly neutralized by 20 milliliters of the 0.01 molar NaOH, that's the base. During this lab activity, appropriate safety equipment is used. That's great to hear for this fictional situation. Good to know everybody's being safe. 78, state the color of the indicator litmus in a sample of the original NaOH. Well, what is the original NaOH? It says here NaOH had a pH value of 12. So we want to see what color would the indicator litmus be in something with a pH value of 12. So let's go to our acid-base indicator chart. That is on page 6. That's where all the acid-base stuff is, right? All the way at the bottom. And litmus, it tells us, turns from red to blue between these pH values. That means anything with a pH value less than 4.5 would look red. Anything with a pH value greater than 8.3 would look blue. And between 4.5 and 8.3, that's where it's going to look some kind of combination. It'll look different shades of purple. Maybe a little reddish purple at first, then like real true purple around 6, 7 or so. And it's going to look more bluish until it gets to 8.3 where it's entirely blue. So because we're looking at pH 12, that's going to be higher than 8.3, so it'll definitely look just blue. No purplish, no reddish. It's just going to look blue. That's how litmus looks in bases. 79, determine the pH value of a solution that has a hydronium ion concentration. That's the acid ion, that's the H3O plus, but it works the same way as H plus. Either way, it's just talking about how strong an acid something is. It's got that ion concentration 100 times greater than the original base NaOH. So the acid ion is 100 times stronger than the NaOH at pH 12. So remember your pH scale. The NaOH was 12, so I'm just going to write my numbers here. We have 11. I should be able to count to 11, not 10. Let's pretend I didn't just write a 10. That's a 10, and this is a 9, and this is an 8, and so on, going down the line. If the acid is 100 times stronger than pH 12, remember, every time we jump 1 unit on the pH scale, it's a logarithmic scale, and it makes a 10-fold change. So 11 is 10 times stronger of an acid than 12, 10 is 100 times stronger of an acid than 12, 9 is 1,000 times stronger of an acid than 12. This specifically said the acid ion concentration is 100 times stronger than the base, which was 12. So that means 2 spots to the left, and that's going to be pH 10. Determine the pH value, it's going to be 10. 80. Identify the positive ion in the original HCl solution. Our boy Arrhenius told us that when acids break down, they split in water as electrolytes. H is what's given off, and that's going to be the only positive thing. So it's just H+. If it was a base, I'm going to write this kind of off the side because this is non-answer. I'm just going to write an example here. But if it was something like the NaOH, remember, bases split with the OH part, that's the minus half, and the other part's positive. Acids like HCl, when they split, the H is where the line gets drawn, where that splits. The H has a positive charge, and the other half is the negative. So because it says the positive ion from HCl, it's just H+. That's it. If you wrote H3O plus, that works too. I believe that was also, let me double check that. It did, yeah, answer key did say we could write H3O plus. You could also write hydrogen ion, you could write hydronium ion. Either way, you can write the words or the symbols, but H plus is the easy answer. 81, determine the molarity of the HCl solution using the titration data. So use the titration data to determine the molarity. So you have to actually do a titration concentration calculation. Not calculation. Yeah, you have to actually do the titration math here. So I'm going to go all the way bottom here. Remember, titration formula. It's on the back page of the reference table. And this question said determine the molarity. So you have to actually do the math. You can't just set it up. Titration was your MAVA times MBVB. So I'm going to fill that in. I'm just doing this at the bottom of the page because I have more room. You would have plenty of room on your answer key. You would have like probably a half a page or so to fill this in. They give you plenty of room for this thing. MAVA equals MBVB. And we have to actually go up to the question again. We're looking for the molarity of the acid. So MA is going to be the thing we're looking for. So I'm just going to fill that MA in because we know we're looking for that. We have to have every other number. So let's see what we don't have, or what we have and what we don't have. It says the NaOH was pH value of 12. That's not a number we use. It says a 10 milliliter sample of HCl, so that's our volume of acid. So that's the VA is 10. Okay, now we have two of our numbers. And it says neutralizing 20 milliliters of 0.01 base, 0.01 molar base. So 20 milliliters is our volume of base, 0.010 is our molarity of the base. So I'm going to fill that in right here. MB is 0.010. The volume of the base, it told us, was 20, and now we have all our numbers. We can fill these in and do some math. You have to actually calculate. As a last step, I always just try to remember to check if I have to kind of scale anything. Our acid only has one H in it. Our base only has one OH in it, so I don't have to like scale anything up. There's no extra H's or extra OH's. I'm going to do my math pretty straightforward, and I'll plug some numbers in. So on the left side, I've got MA times 10. On the right side, if you do your math, so let me make sure I got my paper here and I did this correctly. I'm not looking down there. That's going to be, I didn't write all my math when I did this, so let me double check and make sure I tell you guys the right thing. 0.010 times, that's times 20, so that'll be 0.2. So 0.2 on the right side. And then you want to get the MA by itself, just divide by 10 over here, that cancels out, divide by 10 over here, and we have molarity of the acid, our MA, equals 0.02. Right, that's our answer. Yep. It's 0.02 molar HCl. That is our concentration of acid. So that's our answer for number 81. 0.02 molar HCl. So last 5 questions of the test, you actually have to do like a little bit of math. Not terrible. All right, last 4 questions. Spacecraft sometimes use a nuclear power source that produces electricity from the heat released by the decay of radioisotopes, like we just did nuclear a week or 2 ago. 2 radioisotopes that have been used in these nuclear power sources are plutonium-238 and americium-241. Both the Pu-238 and AM-241 emit alpha radiation and gamma radiation. The half-life of the americium, AM-241, is 432.7 years. Other sources of electrical energy for some spacecraft have been solar panels and batteries. Great. What could they possibly ask us here? Determine the fraction of AM-241 remaining from an original sample after 865.4 years. All right, so this is like one of those half-life questions we did. We used it with the reference table. We would look up what the half-life is. We don't have to because it tells us here. It says determine the fraction of AM-241 remaining, and it tells us right here the half-life of this americium is 432.7 years. So remember, with these half-life questions, we just need to know how many steps it took first. The first thing we need to find out, how many times is this thing going to be able to react, break down over this span of time. So it goes for 865.4 years. That's what it tells us right here. And we know every 432.7 years it's going to break down. So just divide those two, and it'll tell you exactly how many half-lives it's going to take. And when you do, it's going to be 2 half-lives. So it'll be able to break down twice in the span of 865.4 years. Now we can use that information to figure out what fraction remains. It says what fraction is going to be left after it's able to break down twice. So remember, before nothing happens, 0 half-lives. We have just a whole amount. It's asking for fraction. It doesn't tell us like what mass of it you actually have. You just have your whole. If you're running 1 over 1, whatever, but that your whole sample is still there. After a single half-life, it says what fraction. So you're going to have 1/2 of it remaining. That's your fraction. And now after the second half-life, which is all that takes place, that's the end of the story. After a second half-life, only 1/4 will remain. That's your answer. After 2 half-lives, 1/4 of the original sample will be there. Number 83, compare the penetrating power of the alpha particles to the penetrating power of the gamma radiation. So penetrating power, that was like kind of how far do things travel. The lighter pieces, the ones with less mass, travel farther and can get deeper into things than the heavier pieces. They travel slower. So it goes in alphabetical order. You had, it's over here, alpha, and then beta / positron. They work the same way. And then, what was the other one? Gamma and neutron. Gamma's the fancy looking Y. Gamma has more penetrating power than alpha. Alpha particles are where you can stop it with clothing or skin or a piece of paper or anything. Gamma particles are just, or gamma radiation rather, is just energy. It's like X-rays. Gamma rays are like what you need lead or something like that to block out. So gamma has much more penetrating power. And that's all we have to write. Gamma has more penetrating power. You can write alpha particles have less penetrating power. Again, whichever perspective you want to write this from. But gamma is something you have to do a whole lot better to shield yourself from than alpha. 84, complete the nuclear equation for the alpha decay of plutonium-238 by writing notation in your booklet. So this is what it's going to be like in your booklet. Your booklet will give you question 84. I'll write this on the bottom again. Actually, I'll write right here. It's going to say plutonium, like this, Pu with 238. I'm not sure they give you the atomic number or not. I'm going to fill it in. It's atomic number 94. You'll have, just like one of the quiz questions we did, you'll have plutonium here, and that's going to break into 2 parts. And again, I don't remember, does it say in the book? I don't think I checked to actually give it to you this. I think they do actually give you the alpha particle. So I'm going to fill this in here. If you didn't know that what the alpha particle looks like, it's telling you in the question it's alpha decay. So it's telling you this thing breaks down by giving off alpha particles. So worst case, you just have to actually look at what an alpha particle looks like. So that's on this table O. I think they give it to you. I don't remember off the top of my head, but I'm pretty sure they do because I did not write this down in my answer key that they didn't give it to you. But even if you had to look it up, it looks like this. It looks like helium with the 2 and mass of 4, like this. But I'm pretty sure that this is what the question will actually look like for you. And then you just have to fill in the last part, just like we did in those quizzes, just like we did in class. So you start off with a mass of 238. You lose something that has a mass of 4. What's left over is going to be 234 right here. You start with something that has a mass of 92. You lose, atomic number of 94. You lose something that has an atomic number of 2. So your atomic number of the remaining piece is 92. And then you just got to go look up what element number 92 is. You find that on your periodic table. So we go to our periodic table, we find element 92, and that is uranium. So we just write a U. So I'm pretty sure this is the only thing you have to actually answer. I think they give you the rest of it. Like I said, even if you had to fill this in, it tells you right here it's alpha decay. So you just got to go look up what that is if you forget what it looks like. You definitely would have this piece here. I think they give you this, and you just have to fill in the blank. And the very last question, which is good because we're just over an hour here with this last video. Compare the energy released by the radioactive decay of 1 kilogram of plutonium in this nuclear power source to the energy released by 1 kilogram of chemical reactants in a battery. Nuclear things always give more energy. That's it. Plutonium gives more energy. Nuclear reactions give more energy. Whatever. Nuclear power is powerful. That's the whole point. Nuclear reactions give a lot more energy than burning fossil fuels or burning paper or whatever. That's always going to be the answer. Nuclear things give more energy. It says 1 kilogram of each one. Who cares? Nuclear things release a lot more energy than every other chemical reaction. So that's the answer there. That is 85 questions. By this time, it was about an hour here. We took like a half hour on the first 30. I think it's about 40 minutes on the next one. So, I mean, that adds up to a little over 2 hours. That's me. You're going to take your time, but even going through it at a decent pace and me stopping for a long stretch of time to explain stuff, it only took about 2 hours. So not terrible. You're going to get more and more practice with this, and you're going to be good to take as much time as you need, get some right answers. So take a break. We'll go over these. These ones we're not going to go over because this is the explanation, but we'll do some more of these in class. I'll see you in a day or two.